We're going to continue with what we did in the last class, but well, I'll just write down the path integral after you do the path integral for the harmonic oscillator. You're going to get something like this. The kernel for comma 0, t comma 0 means q final t, q initial of 0. is equal to to put is omega This is the answer to this one. It's kind of a long computation which I did. The S comes out correctly, and I could not derive it last class, but it comes out correctly, and we put into the path integral and find the normalization. Then it will give you the right answer which I've written here. With this, let us move. The new question is, how does a Gaussian wave packet given us strike qt at t equal to 0? This sigma is a function of time, so I'm writing sigma of 0. Involved. So we're going to solve this now. So psi q at time t is, so let me write the formula first. Psi at any q t is equal to p. This is the kernel. This is general. This is general for uh, any kernel. Which means to denote that final integrate over all initial points. This is general. For a free particle, we'll have chi, comma, t, t is equal to this is the path integral kernel which I'm putting. This integral by using the same integration which I had shown you earlier. Yeah, this one is going to give you the using this result. I'm going to write it again in better way. I'm just taking this term inside here, and so I got please wait a second. So sorry for it. And then you're going to have the exponential. So this is what it's going to be. Now we are interested in the quantity psi qt mod square of. And we are going to find this is equal to 1 by p5 sigma square half m by m plus cos square p square by 4m square sigma power 4 to the power half summation minus we have minus a square by 4 sigma square 1 by m plus a which p by sigma square n plus 1 by 1 minus cross p by 2 sigma square n. Well, I can write this as a new question. Oh, well, that's fine. And we'll find something here, which is this. We want to look into some structure. So that is why I'm writing it in this way. That is why we are also interested to find a mod square. Thus, we see that sigma square of t can be written as sigma square 0, 1 plus t squared by square. Okay. And if we write this, if we substitute this, then we are going to get the above as this means the same as quantity, and we will find by sigma square exponential of minus df minus a square to sigma square. This is it. You can take for the now. What is the conclusion that we can build from here? There is a very nice. There's a very nice thing here. At t equal to 0, you're going to get the Gaussian again, the original wave function that we started with. And at t equal to some t, you're going to just have this back. This is the conclusion. Now I'm going to state the result. Okay, I'm going to give this as a question. Given for the evolution of a Gaussian wave packet, wave packet under SHO, simple harmonic oscillation kernel, we find sigma square t equal to sigma square 0 cos square omega t plus square by 4n square omega square sigma power 4 sin square omega t and for free particle uh, can sigma remain time independent. And what are the what is the inference for such a case? So you can see that this t is greater than 0, sigma square t Sigma for sigma square t cannot be made 0 for the particle. For simple harmonic oscillations, though, we can make this to be 0. Zero, because this is cos and sine, and these are oscillatory functions. You can choose such a time when uh, when there is no time dependence. Okay, let's see what I mean by that. Okay. So what I'm saying is, choose omega t to be choose. How do you make that as? How do you make that time independent? It's by choosing this as 1. Choose this as 1. When you choose that as 1, it's cos square plus sine square, and that's just 1. And sigma square t is just constant. Is choose h cut by 2m omega sigma square is equal to 1. And that quantity is just 1 square, that is this part square. Okay, now this is sigma 0. So what you're going to see is m omega sigma square 0 is equal to h cut by 2. Okay, and now I'm going to write m omega sigma and sigma cut by 2. Now this is the spread in x. This is nothing but sigma x. And this happens to be nothing but sigma p. And then we see that this is nothing I've shown for you that the Gaussian wave packet, the minimum uncertainty wave packet, using the evolution of the Gaussian packet under the SHO kernel. Okay, let's go to the third question. Third question is we'll do a little bit of perturbation theory. And for that, we have studied something in the lectures of the what was it? The lectures when you're doing functional integration and all, and how we use those kind of del J, why we define the generating functional, and we use this in the path integral J equal to 0, and we get some correlators. Okay, so we're going to use a similar idea, but we'll see more in detail first in the case of quantum mechanics. And then we'll go to field theory and see this idea again. First, when we'll see this thing in quantum mechanics, we'll try to relate that with what we have learned in scattering, because the idea actually dominates there. Just a second, I'll just go through my notes. I want to see that. Okay. So given a Lagrangian to us, suppose we've been given a Lagrangian, it is some L naught minus a very small perturbation. Okay, this is a perturbation. This is the the symbols have the usual meaning. The arguments are q, q dot, and t. And we consider a Lagrangian at this point. Okay. Given, okay, let me formulate the question. And this original Lagrangian is something whose kernel can be worked out. So, okay, because most of the times we do this only. We consider small perturbations and expand. And we see that we get finite series and Dyson series. And, yeah. Fine kernel. This is the question. So I'll consider two Lagrangians. First Lagrangian is the perturbed Lagrangian, which I'm going to write as LP is equal to A0 minus epsilon B. The symbols have their own arguments, so please do not be confused about the arguments. Rather, I'm just going to write as L. I'm going to write this as L naught plus some Q of T times F of T, where F of T is called the source term. Then along with Q of T, it's called the source term. Yeah. Let's go to we'll work with the source term. Sorry, we'll work with the potential term. So the first term is this. You integrate over this and you get some PA of this thing. And now here, you see, these are all definite integrals. These are all definite integrals. These are all definite integrals, and it's on a series. These definite integrals will give a finite value. Yeah. So that means that whatever you are finding here multiplies with everything. But that thing, I'm going to take it inside. This is this. The above becomes 2. First term is just K naught. Not writing the arguments in this one. I'll write it in the other one. So I'm writing F and I to denote these two tuples. Okay. So this is equal to k naught minus I epsilon by h cut. Now I'm going to slice this kernel into two parts. F, QF, and this means QF and this thing. Then QF is F is, and then I'm writing Q. This is a very bad notation. Okay, let's move to the next one. Now this integral ends here. This is nothing but this thing only. Then this, and then plus with the other term also I'm doing the same thing. Here I will take two. So two integrals like dq prime, and k naught will be qf to q, qf to q prime, then q prime to q, then q to qi. That means I'll have three k naughts in the second term plus 1, 2, 3 third term. We'll have dq prime dq k naught of final, and then the prime coordinates q prime k naught of q prime to q k naught of q to q initial. This will be my integral. Okay, press dot dot dot. This can be written as now. I want you to look at this second term. Consider the second term, which is leaving out the minus sign and silence and putting the epsilon by which I'm leaving the minus sign. En, Ef, so there's no integral. Only this term. Yes. Yes. I'm writing it as epsilon square integral initial final times some f of s where f of s is nothing but this thing. F of s is equal to k naught Qa, Tf, Tf, Tn, Tf, Tfs. This is nothing but integral of dq to the power minus s minus h Tf, Tfs. Okay. Now what I want to do is I want to put this in Q, and I will tell you how I'll be able to put it. Okay. Now I'm going to make a diagram. Suppose this is Qi, this is Qf, and this is the Q direction. And this is some midpoint QC. This is Ti. This is Tf. This is Tc. Okay. And then make a path from here to here. So f of s can be interpreted as this this function. So the idea is that I am discretizing when I write the path integral, when I go from the discrete summing over all paths to the continuum, the path integral. The idea is that I look at the discrete paths and I say that, oh, the particle can take any path from here to here. And I'm weighing over this path by some factor of e to the power is and all these things, right? And I can move this also. That is, I'm integrating over all species. Yeah. So I can interpret Fs as sum of the amplitudes of all these paths, all the trajectories. And each trajectory is weighed by V of Qs. Now this trajectory is weighed only at this Q. It is only weighed at P at the instant of time Q of like instant of time S. I've removed the integral from here and I've put only this. This is like summing over all paths and weighed at the moment equal to S. So Tc equal to S. Okay. And it is not throughout whole of the trajectory. At time t greater than S and t less than S, there is no potential. Potential is only, and so V of Qs is 0. So the path between Qi and Ti to Qc and Ts is Ts, and Qc and Ts to Qf and Tf is like that of a free particle. But at this point, there is some potential. Okay. With this idea in mind, what I can write is I can substitute this to be V of C prime T of C. Therefore, I can put this inside. Okay. Now, if I can put that inside, then f of s can be written as integral over d at this point, t naught, f, ts, qc, c, v of qc, qc, t naught, And we'll call this as K1. BA. Okay. So that means, a second. That means so what we have done essentially is we have put this inside here. And to put that inside and have the integral over this dq, like this variable was different, q prime say. We put this in here and made q of s as q prime of s. And so we are going to have this. So similarly, we'll have k2 as however you want. You may want to take the integral. Similarly, k2 is b2a minus I by ph plus k naught bd bd k naught bc ac k naught ca dq d dpd dqc dqc. Therefore, therefore, k full can be written as k naught minus. So I'm writing schematically that k naught v k naught integral. There is an integral. Schematically, there is some potential here. A, B, particle is just going this. This is k naught. Particle scatters and come out. This is this term. K V K naught. K naught V K naught plus A particle goes in V, then particle goes out. K naught V K naught K naught V K naught V K naught. So this is the kernel for interacting for a potential of this kind. Okay? And this is similar to what we do in Born approximation. So it's the full series. It's not the Born approximation. It's actually the Born approximation is the approximation when you take something up to this order, the first order. But it's if you it's the full series. Now you take approximations and studies pattern or whatever you want to, like, up to whichever order you want to. I will look something on post harmonic oscillators. That is the B part. Okay. That is the B part. Reason for taking the B part. Okay. Uh, okay, let me remove this from here. And we'll see it. And now we're going to do something on the post harmonic oscillator. We're going to relate it with we're going to relate it with the V which we have done. So the question is, take the post harmonic oscillator kernel. So now this is a specific case, but the method works for anything where kernel is exactly known. Here we take SHO. The next question. And the reason for taking it is because it generalizes. At this point, I want to stop for a minute. Let me just drink some water and then I'll start again. And also, just give me 2 minutes. I charge my pen and I'll start again. I also have some. Sorry. Okay, now take the force harmonic oscillator corner and relate this with the quartile kernel. The kernel which we studied in okay. So we want to take the Lagrangian, full Lagrangian, as a part which we know L naught plus this is, so let me not change, let me not change. Okay, it doesn't matter to me. It's up to you. Where L naught is. One second. Hello? Hello? Hello, am I audible? Are you listening to me? Can you hear me? Okay. Yeah. Okay, since you have come, I was doing some problems in path integrals. Do you have any questions or any doubts? Can you just write it in the chat? Okay. What is problems in? Wait, let me see again. Yeah, we did some examples in. I did some free particle example. What? Okay. So path integral for a free particle I had done last class. I can quickly go over it if you want to. Should I go over it? That doesn't show you. Okay. Hmm. The notes are. Okay. Hmm. Wait, let me just see. 7. Let's see. Okay. So, yeah. So for a free particle, okay, let us go over the free particle. So the free particle Lagrangian is like this, and you have been given the boundary condition as Qi is your final initial position. Q of T naught is Qi, Q of T is Qf, and what is the equation of motion and its solution? The equation of motion for a free particle is Q double dot is equal to 0. So your solution, general solution is this. Yeah. And then you put in the boundary conditions, you're going to get A and B as this. All right. So I have just written A and B properly, they're like expanded and written. Now you want to compute what is the classical action. The classical action can be written as half m q square, q dot square, but now you put the classical trajectory here. Okay. The classical trajectory q dot square is nothing but q dot is a, so it's just a square. So this is a, and I have just put that. So dt should be here half m a square, and I have integrated, since a is just a constant, the integral gives me tf minus t0. So my S classical is this. The action evaluated over the classical path for a free particle is given as this. Okay. So clear till here? Okay. Let's carry on. Now you know this kernel meaning the Green's function or 2-point function, has the property of this kind. It is you can write, this is nothing but the kernel between the final and initial points can be written as, you take a point in between, you integrate over the point, and it can be broken in this way. Okay. So this is a property of the kernel. So I'm going to use this property to find the path integral. So kernel is found by path integral only. So this path integral of the free field, kernel final minus initial, final and initial, is equal to dq e to the power I by h cross is classical. This thing actually evaluates to some normalization factor into exponential of S classical, I by h cross S classical. Sorry, like this is whole S. S classical, by S classical, I mean you have evaluated over the path. Okay, this is what you get. Okay, this is a result, and I have proved this result also. Let us go over the proof of this result later, but you accept this for now, and we'll carry on. Okay. And so you can write kernel of AB as NAB is this thing. For a free particle, this is just this. Now we want to know what NAB is, what the normalization is. That is what we have to find out, and we have got our KAB fully. Okay. To find NAB, we are going to use this, the property of the kernel. Okay. So the property of the kernel says that you break this, you can break the kernel into two parts, and you can put a point in between, and you're going to evaluate over all points. Now what KFP is? KFP is just NFP e to the power. Wait, let me just use the laser. Yeah, you know what this thing is? Sorry, sir. So you know what this is? This is just NFP e to the power QF minus QP. Okay, minus by TF minus TP. So NFP e to the power, this part is this, and this is KFP. All right. Now I'm going to write the same thing for KPI. This is this part and this part, the exponential and this part. Okay. These are normalization factors. So they come out of the integral here, and you have the integration as this. Now I've just done the integral of this thing. I break the square. I firstly break the square and then complete the square with with the QP term is like this, and whatever is left over I put it in alpha and alpha square. Alpha does not depend on QP at all. Okay. When I do this integral, I'll evaluate the integral to this. That is this. Now you can observe from here, this cancels with this term. And so I'm going to get NFI, NFP. The NFI is equal to NFP times MPI to this term. Okay. Now from here, you have to conclude what is the form for NFP or NPI. What do I choose for this so that this equation is satisfied? All right, clear till here? Or any doubts? Clear? Okay. Now, you choose NFP as this thing, okay? You put it in this part, and NAV, like this is the general thing which I have written. You choose NAB as this part, you put it here, like you substitute FNP, and you put it here, and you are going to find that you get an expression for NFI, which looks the same as this. Like put F and I here, which looks like this. Okay, so that means that means you know that NAB like N should be of the form this. So now let us go back to our full kernel. So in the full kernel, we are just going to write what we had. This is just, this should have been final F and I. And this should have been F and I because we have F and I here. So this will also be F and I. And so we are going to get this as the normalization. So this is our free particle kernel. Okay, this is how we find. You can do the same thing for the harmonic oscillator also. And I was finding Green's function. Harmonic oscillator, I was doing it, and I had stopped because some calculation went wrong and it was getting a bit tedious. So I left it in the middle and I went on to do other things. Yeah. Okay, you're clear? How to find the free particle kernel? You have to do the same idea for the same thing for the harmonic oscillator if you want to look at it also. Now I was talking about perturbations. Okay. Any questions? You have any questions? Do you want to ask? Any doubts? How do we get the integral expression? But how do we get the integral expression? Integral expression of what? Okay. Solution to the path integral. Wait a second. Wait a second. Just wait a second. Wait a second. Yeah, I'll show the proof. Yeah. So how do we get the expression for the path integral? So yeah. So okay, let me show the proof for that one. Okay, this is the proof. Suppose I give you a general quadratic Lagrangian of this form. Okay, look, this is very general. It has got q dot square, q dot, q dot, q square also, q, f of t, b of t, a of t. You can choose anything. To make a harmonic oscillator, you choose a of t as half m, and you choose this to be 0, this to c to b to be 0, c to be 0, e to be 0, f to be 0, and dt as minus half m omega square, right? And you are going to get harmonic oscillator. So this is for a very general Lagrangian, okay, of this kind. You can choose for a free particle, you choose all these to be 0, and you just have this to be half m, right? Okay. Now we have this Lagrangian. We'll find the equation of motion as we did in the case of the free particle. This is the equation of motion. We find the equation of motion as this. This is the equation of motion. And we are going to say that this QC is a solution to this equation of motion. That means if I put QC here and evaluate the left hand side, I am going to get the right hand side. Okay. Now I am going to consider fluctuations of QC. This is QC, the classical trajectory. The fluctuations are, say, given by eta. So eta means how much it deviates from the classical path. In fact, that is what the idea of the path integral is, right? That we sum over all the paths. So I'm starting over the classical path and I'm considering its fluctuation and I'll sum it over. That is what I'll do. And then I'll sum it over. But I'll put the condition on this field eta is that this function eta, that it should vanish on the endpoints. So eta of A and eta of B, it should be 0. Okay. So Q can be written as Q classical plus eta. Now my Lagrangian, I'll write it as Q classical plus eta and all these things. Okay. I'm just substituting for it. So when I substitute, I'm going to get a big term. I'm just opening all the terms here. And I am putting the terms which are which was already like, you know, with the, so the same, the Lagrangian with QCL, I'm calling it as LCL. And this is this term. Okay. So that is all these terms, this term, this term, this term, this term, this term, this term, that comes in L of Q, L of CL. And whatever is left, I'm writing it down. This is this term. Okay. Clear till here? Okay. Now, what we are doing is, I'm putting this part here, and this part I'm written here. And this part, for this part, I'm doing a manipulation. It's not a manipulation, it's a manipulation. So what I'm doing is I'm taking the derivative of, actually it's this part, okay? This thing is actually this part. So I'm taking the derivative. So this term is this term plus this term combined. If you have this term, you're going to have eta dot, this term equals eta dot times this whatever there in the bracket plus eta times 2a q double dot plus cq dot plus b. Okay. And so this term will give you eta dot into whatever there is in the bracket plus eta into 2a q dot this thing. So I am subtracting from this term the 2a q double dot wala term. So this minus this will give me this term. All right, clear till here? Clear till here? Okay. So yeah, this minus this gives this term, and this term is this term. Now I'm going to have, yeah, now this term I will write it together. That is d dt of this thing. So eta I have taken common, and d dt of this thing plus this thing minus d dt of this thing. Okay, and this is nothing but this equation of motion, because our equation of motion was, what was it? It was this 2a q dot 2a dot q dot 2a q double dot b dot c dot q, and you're going to see the same thing here, which is 2a q double 2a dot q dot plus 2a q double dot plus c dot q plus cq dot plus b dot. Right. So we have the same thing here. So we have the same thing here. Okay, this is nothing but this term. Okay, and the other part is nothing but this term. That is this part. So this is nothing but equation of motion only. This I have cut here, here, and reached here, and this is the same here. If you see, so this part is nothing but equation of motion. So I have written it like this. Okay, so I have written a plus b satisfy equation of motion. So a plus b. So this term is 0 because equation of motion is equal to 0, right? What I mean to say is that if you take this on this side, you have this minus this, which is equal to 0, or minus this plus this is equal to 0. So I have done the same thing. Plus this minus this is equal to 0 using the equation of motion. All right. So I'm going to get this term is 0. So I will have L classical plus this thing plus this thing. So that is L classical plus this thing plus this thing. Now I want to compute the action. The action is integral from initial to final point L classical plus this thing plus this thing. Yeah. Now this is a total derivative term. When you integrate, you just have to put on the limits. And we had our condition that eta at the endpoints are 0. So at the endpoints, this term, it is 0. So the integral of c is 0. Clear till here? Are you clear? Yes. Okay. This is 0. So your integration S is nothing but this part. And this part, this term is nothing but classical action, because this is over the classical path. So you are going to look into the path integral, which is this. This path integral is something which is like, this has a, this measure can be, so this dq can be written as like this. You take the limits over n. There is some normalization factor which depends on n and e to the power is. Okay. So when you change all the small variables from qi to eta I, your Jacobian of transformation is just 1. So there won't be any extra factor which you'll get here. So you can safely change dq to, or these things to, d etas. Like you can change this thing to pi over I from 1 to n d eta i's. And this pi over this thing, what I had just written, can be written as like this. Okay. And I put this thing. I now put the action S. S is just S classical plus this part. And S classical is here. And the other part is here. Now, S classical has been already, evaluated. So this part just comes out. And you're going to have the integral, the path integral over this part only. This part only has this part. Okay. So you're going to get this. So you see this part. So the whole of this path integral boiled down to this thing. You just need to evaluate the classical action and you have to just calculate this part. And this part is where the normalization comes in. Okay, when you do the integral of this thing, it's nothing but the normalization. Okay, because this will give you some finite value and this is nothing but the normalization. Now let's see what happens for the free particle. For the free particle, C and D are 0. And you're going to have, for the free particle, B, C, D, E, F, everything is 0. Only E is there. So you are going to only have this. And this is nothing but your normalization, because this is a finite integral and it will just evaluate to some value. So this is just nothing but the normalization. And so your answer can be written as some normalization into e power I by h cut of S classical. And you have to find this normalization somehow. You may do the path integral again if you know the answer to it, or you may use what I had been doing. Consider this as normalization and use the idea that the kernel can be broken down into two separate kernels with an integral over the internal point. Okay, you're clear now? You're clear. So this is how, using this, I solved the path integral for the harmonic oscillator. Okay. Any doubts, any questions? Maybe, are we supposed to be able to solve path integrals on our own for different perturbations? So I don't understand your question. Like, you see, when you have perturbations, generally when you have perturbations, so by the way, what is your, have you done uh, uh, quantum mechanics too? Because I was just telling about perturbations only. So I just wanted to ask, quantum mechanics too, where you study scattering. Have you studied scattering? No, okay, not scattering. Okay. So I see. That's good. Yeah. For different, but there to solve for perturbations, there is a way. So the way to solve for perturbations, you may not be able to solve anything exactly. Okay. So that is why what we do is we do some kind of a series expansion. That is what I was talking about here. Just 30 minutes back, I just did this question. Suppose you have been given a perturbation of this kind. This is a perturbation to the original Lagrangian whose kernel we know. For example, we will take simple harmonic motion in the next question and we are doing something. So the perturbed Lagrangian is something like L naught minus. This is L naught, which you know how to solve. This may be SHM or free particle, whatever it might be, for which the kernel you know, minus epsilon V. So K can be written as like this, and this is nothing but this S naught is for the L naught part, and epsilon V is this part. Now I'll expand this. Okay, this is nothing but the kernel for the Lagrangian which you know. So you are going to have this kernel minus kernel is already evaluated. It's not a function of S. So I'm putting this kernel inside. So this is kernel. This is a finite integral. You'll get some value. All this is a finite integral. You'll get some value. So kernel is here. It gets integrated and it goes inside. Okay. So I have put this inside the integral. Kernel is put inside the integral. Now I use the property of the kernel to break the kernel into two kernels with the integration over the internal point. My internal point is q prime. Q prime at t, q prime at t, qiti, qfti, dqs. Similarly, I have done it for the third term also, like this, plus dot dot dot. Now let us consider the second term, this term, okay? Consider this term. Hey, are you being able to follow this thing? Because I feel I'm going a bit fast since you have you don't have much knowledge about. You've seen this before. Okay, this is correct. So you're going to get this. Okay. So now consider the integral. Consider the integral. Consider the integral of this kind, where you have this. So wait, what I was going to do was consider this thing. So we'll consider this and we'll write this function as f of s. Okay, that is what I have done here. So f of s is like this. Now your k naught is nothing but integral over this, which is some s naught d over dq, and you have d of q of s. This is different and this is different, evaluated differently. But now I am going to argue that I can put this inside. Like, I can think of this q as being in the same q here. And the way to argue is this. Now, when I write this function as f of s, I am fixing a time s and I'm looking at the potential. So q of s will give me some value. I'm looking at the potential. So q of s, suppose, gives me qc and qc, and this is t at s. This should be s, okay? So it gives a value some qc. Okay. Now, what does this integral mean? This means path integral. If you were to break the path integral, when when you utilize the sum over all paths of the path integral, you break over paths and you have sum over all paths to get the path integral. You have this idea, right? You have this idea, you take different paths, all these things in between, you do something, and you get the expression for path integral to be something like this. So when you do that, when you go back to that derivation and think, you have those discrete paths and you are having this potential at a point in that path. Okay, at a point in that path. After this point, after this time, there is no potential. Below this time, there is no potential. It's only at that time there is this potential in that path. That is why I can take this QC, I can take this V inside. Like I can consider this Q to be an internal point. If I think like that, when I break the path integral, when I break the kernel into two parts, I can put it for that QC. Okay, I can put it QC here and integral over QC. Earlier, this V was outside and only we had this part, and the integral gave us integral over final and like K naught of UF, like final point and K naught of final and initial integral. Sorry, integral over dt. So I was just writing this expression actually. Integral over ds. This part I have broken down into two kernels and I have put this point in between, and the breaking down of the two kernels, I have the integral, right? The same point I have put in the integral. With this logic, I am able to do that. And I'm just doing that only. So I can write K1 as something as this, and QC, integral over QC, it goes from minus infinity to infinity, and DTC as we had in this thing. The dt is for this ds, okay? All right. So using this, I will do this for this. I will do this for the other term. The limit should be appropriate. I'll just put in this thing. This is here. And now I can write this as, okay, there should not be any, sorry, there should not be any integral here. Oh, sorry. This is, there should be an integral. So this is K naught, right? So this integral is there, integral is there. And schematically, you can think of this as a, this term can be thought of as particle comes from an initial point A, goes to the final point B. There is no interaction in between the potential. This term is thought like that. The interaction is once. That is why we have given a zigzag line. For this, the interaction is twice. Once, the free particle gone inside, interaction, scattered, interacted again, scattered, and then came out. Or like, sorry, this should be like came out. Like went inside, scattered, and then went, again scattered. So this is for went, scattered, went, scattered, went. Went, scattered. It went inside, K naught, scattered, that is V, and then went this side, this is K naught, again scattered, and then went outside. So this is like this. So you probably didn't see it, right? So what I was saying was, it went inside, this is K naught, it scattered, and then went till here, it is K naught, again scattered, and then went out. Okay. And this kind of picture you see when you study. So for example, what is the book which you are studying for So the series expansion is just yeah. Mostly, yeah, it is the complexity of scattering we are willing to entertain. That is like when you are doing quantum mechanics, there is you don't have an idea of particles being scattered. Okay, the idea is there in quantum field theory. So here scattering has other meaning. You just think of the like when you're going to study scattering in quantum mechanics. So what is the book which you are using? Are you studying Griffiths, quantum mechanics? Griffiths and Sakurai. So when you study Griffiths, there's this chapter called scattering, and the idea is that the scattering, this series is a schematic. You don't think that a particle is coming in and out. It's like think of a wave, uh, e to the power I k z. It comes, scatters, and then goes out. Now there is the complexity of scattering. If you're talking in this way, then it's fine. It's right what you're saying. So there is this idea of Born approximation and all these things, which you will study later, and which is there in scattering. This is QM. There's no QFT. We're doing quantum mechanics now. Path integral in quantum mechanics. Yeah. Okay. So we are doing some question. I totally forgot what was in the question. It's better you ask doubts. There's only 15 minutes. By the way, where are you from? Like which institute? Oh, I see, I see. Good, good, good. Which year? Third year. I see, I see. Okay. Physics. Okay. All right, all right. Okay, so you got anything, any doubts, anything else? 15 minutes we can discuss that and I can end the class. Okay, okay. Take your time. So creation and annihilation operator in which context? Like the field theory. So you have say if I say harmonic oscillator, field theory creation and annihilation. No, you are not doing second quantization. The notion of second quantization is kind of wrong. Okay. So this idea of second quantization, it doesn't. So this we'll do at probably the next class. So the notion of second quantization is not a correct notion. Okay. So in the sense of what I'm going to tell you, and you have to respond to me. Hey, it was better if you had a mic. Can you do something about it? If you can, just do it. Better if it's interactive. Okay. No, I can't hear you. Can you speak? Just speak. I don't think so. You're not. You're still. Can you just stop? Hello. Hello. Okay. 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 Very good. Okay. So what is the meaning of quantization? Okay. Meaning of quantization. You have classical mechanics. How do you go to quantum mechanics from classical mechanics? Do you know the answer? Can you tell me, or how do we go from classical mechanics to quantum mechanics? Can you just write it down? Quantize operators and create a formalism where we get eigenvalues, observables, and such. Okay, that is somewhat correct. But the idea is this, okay? In classical mechanics, you have Poisson brackets. You promote them to commutators. And I guess IH. But in classical mechanics, you have phase space. In quantum mechanics, phase space tells you all about the what do you say, position, momentum of the particle. And in this case, you have Hilbert space. There is a notion of phase space in quantum mechanics also, but we will not think about this. Okay, the main point is, whatever the main point is this. Okay? You promote whatever is inside here, you promote this, the Poisson bracket is a function of the phase space. You promote them as operators, whatever is comes inside as operators, and you get some commute, whatever was the result of the commutation relation, you are going to have the same result. For the Poisson bracket, you are going to have the same result for the commutator. You have 1 by IH cut goes that way. This is what it means when you quantize things. Okay. This is when you go from classical mechanics to quantum mechanics. Now, you have a classical field theory. The classical field theory. Classical field theory. Now you want to go from classical field theory to quantum field theory. You're going to do the same thing. Got Poisson brackets, it evaluates into something. You're going to promote this into commutators. Okay. You had some phase space, you're going to promote it to Hilbert space. The same idea, the same logic, it works. Okay. Now, now, in this way of thought, which is the correct way of thought, okay, so in classical mechanics, you have positions as functions of one variable, which is time. Classical field theory, you have field. For example, like electric field, which are functions of positions itself. So and also of time. Electric field you have magnetic field or like gauge fields and all these things. Okay. Now you can write a Lagrangian for the classical mechanical system. You can write a Lagrangian for the classical field theory system also. For example, in this case, you get you say you have a field F1. This is a function. Since it is a field, it is a function of x, y, z. And when you take the Poisson bracket, you take at only a fixed time, a section like, a time, a fixed time. So you fix the time, Fy, x, z, some t naught. You have a field F2, which is a function of, this is say x naught, y naught, z naught. And this is say x1, y1, z1 of t naught. It is at same time. And suppose this gives you Dirac delta. Say this, I'm saying it as x naught vector. This I'm saying it as x1 vector. Dirac delta of x naught vector minus x1 vector. That means there are three Dirac deltas here. And I'm writing vectors in. Okay. Now you will promote this thing as a quantum. Now you want to promote the theory into a quantum mechanical theory. You are going to write as F1, F2. This is at x naught. I'm dropping the t, okay? These are equal time commutators. This may be different space, but they are equal time. And you're going to write, it's an IH cross, similar type of expression. Yeah. Now what you're going to do, for example, if this is a Klein-Gordon theory, your field one is phi, the phi of x at the same time t. The other one is the momentum, field momentum, y at the same time t, but different position, different space position, x and y. I'm going to have say IH cross Dirac delta of x naught minus x1. You're going to expand this and you're going to see what happens to the operators. Like you are going to mode expand the field. Mode expand phi and phi and see the relation to the commutator relation of a dagger, and you can derive it from this thing. This has been given to you. You see what should be the commutation relation of this thing. Say it is like 1. What should be the commutator of thing? There should be k and all these things, k and k prime, and it should be delta k, k prime. I'm not worrying about that. Okay, I'm just telling you what it means to quantize. Okay, this should be 0, and all these things you are going to find. Mode expand and find the commutation relation of these parameters of these creation operation. Example commute of creation is annihilation operators. Okay. So when you're doing this, this means you are looking at how these things are. Okay. Hmm? So where have you done second quantization in this process? When you are saying second quantization, where have you done the second quantization? Are you clear in what I'm saying? You understood it? Hmm. So you have not done any second quantization here. Okay. What you are doing is you started with classical mechanics and went to quantum mechanics. Now you're starting with classical field theory and going to quantum field theory. You're doing the same procedure. This formalism is called canonical formalism. The other formalism is the path integral. Okay. So you have not done second quantization anywhere. Second quantization literally means to quantize it the second time. And this has no meaning here. Like, in the whole process of what I said to you, yeah, it doesn't mean anything actually. So second quantization is a name which got stuck because, what they were doing was, somebody wrote Lagrangian for the Schrodinger equation. Okay, so Schrodinger equation was already given, and somebody cooked up a Lagrangian which gives the answer which gives the equation of motion as the Schrodinger equation. Okay, so now they are saying that okay, finding the Lagrangian, finding the equation of motion is a classical mechanics process, and this is giving a quantum mechanical equation, which is the Schrodinger equation. Okay, since this is a quantum mechanical equation, if I quantize it, it will give me I'll quantize it the second time. So that is why the second quantization name stuck. But second quantization doesn't mean anything. The way in which you are finding the Lagrangian, right? So there is some Lagrangian, I don't remember, some Lagrangian. There is some Lagrangian whose equation of motion gives you Schrodinger equation. Okay. The Schrodinger equation looks like minus h cut square by 2m del square in one dimensions I'm writing. Okay, let's write in 3 dimensions only. Del square psi. Now this psi is a function of x, y, z and t. Plus v, say this is only x, y, z, psi x, y, z, t is equal to I h cut del t psi x, y, z, t. Right. So there is some Lagrangian whose equation of motion will give you this equation. There is. But the problem with the interpretation is that this is no longer interpreted as a wave function. This is to be interpreted as a classical field. When you are doing this kind of procedure, even though it gives you something which looks like a Schrodinger equation, this is not what the interpretation of Schrodinger equation is. This now is thought of as a classical field. Now, when you quantize this field by writing, say, field and its momentum, and you are finding mode expanding and mode expanding here also, and you're getting something like AK dagger is equal to 1 or anything, whatever the result is, Hmm. There should be delta, it's actually delta K minus K. So whatever result you are getting, you you say that you already had a quantum equation and you quantize the quantum equation. That is why you are getting the Schrodinger equation. So, sorry, that is why you are doing second quantization, because you quantized an already quantized equation. Okay. That means you are writing mode expanding this. So people say that you are mode expanding this. That means you are doing second quantization. No, not at all. That is wrong. When you are doing this Lagrangian, which gives you a Schrodinger equation, this is a classical field in that equation, which somehow looks like a Schrodinger equation. Okay, that is the idea. That is the catch. Okay, any more doubts? So, okay. Thank you. Thank you for joining in. All right. Okay, let me end the class here. Pranav, will you join us next class also? Because, nobody had been coming to my class since last three lectures. All right. You two have a good night. Okay, bye. Ending the meeting.